Hi, welcome to Sam's Maths Lectures. This is my 5th lecture on group theory now. So if we take two groups, G and H, the groups, and sum phi from G to H, a homomorphism of groups, then we can define the image of phi as this set im phi, which is the set of all elements H in H, which can be reached from G. So there exists some G in G such that phi of G is equal to H. Okay, so if we let H equal phi of G, H prime equal phi of H prime, both belong to phi of G prime, both belong to the image of phi, then H, that primed inverse, is phi of G, phi of G prime inversed, but because phi is a homomorphism, we then have that this is phi of G, phi of G prime inverse, which is phi of G prime inverse, and so belongs to the image of phi, which must then be a subgroup of H. Okay, we have that if phi is surjective, so it covers H, then we must have that the image of phi is equal to H. And if it's the trivial map, so every element is mapped to the identity, then the image of phi is just the identity, so the trivial subgroup. Okay. We also have a second set called the kernel of phi, and that is the set of all elements which map to the identity. Okay, so kernel of phi is written ker phi, and that is the set of all G and G such that phi of G is equal to E. Okay, so let's have G and G prime in the kernel. Therefore, phi of G primed inverse is phi of G, phi of G prime inverse, and that's just E inverse, which is E. So G prime inverse is in the kernel of phi, which must then be a subgroup of G. Okay, and then we can take this further. Let G be in the kernel and H be in G anywhere. Then we have that phi of H inverse G H is phi of H inverse E phi of H, which is just E, so H inverse G H must be in the kernel, which is then a normal subgroup of G. Okay, so if we take two elements, let G and F have phi, two elements of G, have phi of G equal phi of F, then that means that phi of G inverse F is equal to the identity, so G inverse F belongs to the kernel of phi. And so that means that if phi is injective, then suppose there exists some k in the kernel of phi, then we have that for all G in G, phi of kg is equal to phi of G, but because phi is an injection, we must then have, therefore, k must equal the identity, so the kernel of an injective map is just the trivial subgroup. And if phi is trivial, then we must have that the kernel is the entire group, because every element is mapped to 0. Okay. So we can now factor out the kernel, because it's a normal subgroup, so we can take the group G over kernel of phi, okay, and we're going to create this new mapping, phi star, which is sort of an induced mapping from G quotient kernel to the image of phi. Okay, and the way we're going to do this is we're going to map G times the kernel is going to just map to phi of G times, just phi of G. Okay, so this is our map. So first let's show that it's well defined. So suppose G cur phi is equal to G prime cur phi. Therefore, G prime inverse is in the kernel of phi, and so therefore phi of G must then equal phi of G prime, because phi of G primed inverse is equal to E. Therefore this, and so phi star of G cur phi is equal to phi star of G prime cur phi. Okay, so the label of the group doesn't matter, so it's well defined, that's important. Okay, we now need to check that this is a homomorphism. So we clearly have that phi star of G cur phi G dashed cur phi, using the product of the equation group, is phi star of G dash cur phi, which is phi of G dash, which is phi of G, phi of G dash, which is then phi star of G cur phi, times phi star of G dash cur phi. Okay, so phi is a homomorphism. Okay. What do we have next? So suppose phi star of G cur phi is equal to phi star of G primed cur phi. This means that phi of G is equal to phi of G prime, which implies that, of course, G primed inverse belongs to the kernel of phi, and therefore we have that G cur phi is equal to G primed cur phi. So phi is an injection, it is injective. And finally, for all H in the image of phi, there exists some G in G such that phi of G is equal to H. So there exists G cur phi in G over the kernel, so, and not even exists. So then we can take G cur phi in the kernel, in the equation group, and we have that phi star of G cur phi is equal to phi of G is equal to H. So phi is surjective. So now phi is a well-defined bijective group homomorphism, so phi is an isomorphism, And so this gives us the first isomorphism theorem of groups, which is that for any homomorphism phi between two groups G and H, G over the kernel of phi is isomorphic to the image of phi via phi star. Okay, so this is the first isomorphism theorem for groups. There's also a first isomorphism theorem for sets, for rings, for modules, vector spaces, and so on. And they're all sort of the same sort of thing. Okay. So we can now introduce an object sort of called a sequence. Okay, so a sequence is a collection GI and over some indexing set I, usually I is some subset or equal to the integers or the natural numbers, and homomorphisms phi I over the same indexing set or some subset of, such that phi I is a homomorphism from G of I minus 1 to G of I. Okay. And so we can sort of express this as sometimes sort of G0, which goes via phi 1 to G1, which goes via phi 2 to G2, and so on. Okay. So a sequence is exact. If for each I we have that the image of phi I is the kernel of phi I plus 1. Okay, so what this means is that therefore phi I plus 1 of phi I is always equal to the trivial map 0, we can call it. Okay. So a sequence is then called a short exact sequence if we can terminate it with the trivial group like this, and it's exact along the way. So we can do G here, G twiddle, we'll call this psi, and then 0. So this is just the trivial map, so including the identity into their group. This is again the trivial map that crushes that. Trivial. Okay. And so we must have that we'll call this T1, I guess, and T2. T1 is equal to the identity, which must then be equal to the kernel of phi. So phi is injective for a short exact sequence. I think I said it, but I can't remember. Okay. Then we have that the image of phi is the kernel of psi, and then we must have that the image of psi is the kernel of T2, which is all of G twiddle, so psi must be a surjection. Okay. Now what that gives us is that for any subgroup n of G, we can take 0 and then we can map that to n just by the trivial mapping. Then we can include n in G, using sort of the inclusion here, and then we can map this using the sort of canonical mapping onto the quotient group G over n, and then we can take this back to 0. Okay, so this allows us to, this is short and exact, so we have that clearly an injection because it's an inclusion. Each member is mapped to itself in G. Then this is a surjection because that's just how the quotient group is defined. It would be impossible for it to be anything but a surjection. And then we have, for all n in n, phi of n is equal to nn, which is en. So we have that the image of iota is indeed the kernel of phi. Okay, so that's a short exact sequence. Okay. If we then take two normal subgroups n and k, which are subgroups of G such that n is itself a normal subgroup of k, or we can say n is a subset of k, which gives us that n is indeed a normal subgroup of k. Then we have a map phi G over n to G over k, which maps Gn to Gk. Okay, and so the image of this subgroup is G over k. And its kernel is going to be, ooh, did I do this the wrong way around? We go from gk to gn, sorry. Here we go. And then obviously that's a surjection now because every element of n is, oh no, it's fine. Okay. So the image is G over K because we can just plug in any G and we'll get that. And then the kernel of phi is the set of Gn in G over n such that Gk is equal to Ek, i.e. the set of Gn in G over n such that G belongs to K. Okay, and so that is in fact the set K n, where K is in K, which is then the quotient group K over n. Okay, so what this means is, using the first isomorphism theorem here, we have that G over n over K over n is isomorphic to G over K. Okay, there we go. So this is interesting because we've been adding and dividing groups in a way. So we sort of have this product, and then if we take the trivial group 0, then for all G, we have that the direct product of 0 and G is isomorphic to G itself, and that's isomorphic to 0, G times 0. Then we also have that for all groups F, G, and H, we have that F times G times H is isomorphic to F times G times H. Okay, and then we can sort of do this other operation. We have that G quotient G is always isomorphic to 0, and G quotienting out the 0 subgroup is always isomorphic to G itself. Okay, so basically what we've ended up with is that groups themselves almost form a sort of group. We've got an associative property, we've got an identity element, and then we have sort of divisibility when we have normal subgroups. Okay, which is an interesting thought. Okay, I think that concludes this lecture. Thank you for listening.